Hi everyone. Today we'll start our discussion on axial loading, part 1 out of total part 2. Before talking about axial loading, let's review the concepts we covered in previous lecture. So in previous lecture, we delve into the details of stress analysis in connections and factor of safety. As I told you, um, you know, in addition to like typical tension and compression, discussion we have done back in general physics, because we are now considering deformable body and realistic material which can break, we have to focus on like the stress state in the connections and pins and etc. So one example we considered was the rod BC, which was under tension. So there is rod BC which is under tension, and if you think about to give some tension on the rod BC, you have to make a force at these 2 points, right? These surface, and you are pushing the body in these two surfaces, okay, during using the pins, right? Now if you make a imaginary cut here, what you can find is that to balance force acting on this surface, you need another force you know to balancing out this. However, when you think about boom AB, and if you look at at which surface is under force, subjected to the force, you can see that these surface is under you know compression. Now if you make an imaginary cut, what you can see here is because this is the only thing, only place that you are giving force, and in the opposite direction you have these point where you have a force. What you can find is that you don't need any force acting here, okay? And if you look at the volume here, if you focus on this imaginary volume, what you can see here is there is no force acting on this imaginary yellow volume, okay? So you don't need to worry about safety here and there. In contrary, we had to worry about the I would say health, structural health of these parts where we have a relatively similar cross section. In addition to these connections, we have to also consider this bearing stress for pins and shearing stress for pins. Okay, so these are the details discussions we have done in previous lecture. So the important thing you have to learn is you have to learn how to draw a free body diagram for any parts. Like you have to use divide and conquer strategy for any part of the body. So when you see let's see, when you have any arbitrary shape of the body, what you have to do is you have to practice and try to see after making this imaginary cut if you can draw free body diagram for this part, free body diagram for the other part. Okay, so what you have to do is in addition to physically divided the part, in your head you can make an imaginary cut, and for each imaginary part you should be able to draw free body diagram. So it requires a lot of practice, and even though it's quite tedious to solve homework problem, I highly recommend you to solve all homework problem by yourself so that you get familiar with the concept of drawing free body diagram. Actually, the free body diagram practice must have been done back in freshman physics and high school physics, but even though you didn't study hard in freshman years and in high school years, if you do this practice very well, now you can do solid mechanics quite well, even though you didn't do very well in general physics course. Okay, so please do a lot of practice, even though tedious. Please do practice, and it will give you opportunity to learn mechanics efficiently. In addition to this stress analysis and connections, we have also discussed about factor of safety concept. Even though we use the concept factor of safety, it's nothing. So even though the material's ultimate strength is, for example, 100 megapascal, if you design your structure with maximum stress of 100 megapascal, you don't have any buffer, right? Because there can be dynamic loading, there can be mistakes in designs, there can be mistakes in material manufacturing. However, even though the material ultimate strength is 100 megapascal, if you set your allowable stress in your design as 70 megapascal, you have plus 30 megapascal of some sort of a buffer, right? With this kind of buffer, you don't need to worry about possible huge dynamic loading, possible mistakes in design, and possible mistakes in manufacturing. A lot of mistakes can happen, right? So you can think about factor of safety as leaving sort of a buffer to ultimate material strength. Then it'll give you better understanding on the concept of factor of safety. And as I told you, if you think about like a old ancient Greek and Roman structure made out of stones and rocks, the factor of safety for those buildings are huge, and that's why their pillars and walls are so thick at that time, because they don't have specific characterization of the material property, and they don't have like a variety of structural material we have now. They only have like a stones and like a elementary level cement and etc. So that's why they able to use a huge factor of safety at that time, and that's why the windows made out of those ancient buildings such as Colosseum is much smaller than the windows that modern buildings have. Like if you think about like the tallest tower in Korea, the Lotte Tower in Korea, you can see that building has some minimum bone structure out of the steels and a little bit of concrete, and you can see huge walls decorated by glass, which was of course impossible back in old days. Okay, so hopefully you have some sense on factor of safety after this discussion. Then we discussed about stress on oblique plane. In the first lecture, we discussed about stress in this perpendicular plane, but when we have some oblique plane with angle theta, we have to define the force acting on here and the area change here. Then what you're gonna see here is the normal stress and shear stress somehow have cosine square and sine theta cosine theta term, which you have not seen in your life, right? Because you've only seen like a vector quantities until freshman years, and you never get exposed to tensor quantity. It looks quite weird, but please remember that stress is a tensor quantity, and that's why it does not follow typical vector transformation rule. Regarding the detailed discussion about tensor, I recommend you to take the advanced solid mechanics course in graduate school. I think it's ME 530, and you're gonna get a much better detailed discussion on the tensor quantities. Then we discussed about stress under general loading. So when you have some continuum potato, and if you try to make a imaginary cube inside this continuum potato, and there can be like a 9 maximum component of stress, like a 3 normal stress, XX, YY, and GG component, and like a 6 shear stress component, XY, YX, XG, GX, and GY, YG. However, due to this mechanical equilibrium constraint, so that you can satisfy force equilibrium and moment equilibrium, out of 9 components, only 6 stress components are independent to each other. So when you have to determine the stress state of arbitrary infinitesimal cube, you have to worry about only 6 independent components, and the other stress component, shear stress component, will be automatically determined by these, because they will satisfy this relationship. Okay, so with that, let me finish a small review for our last lecture, and hopefully you have like even better understanding with this short recap video. Okay, so now let's start discussion on new concepts.